All right, thank you. Thank you, Veronica, for organizing. Thanks, KITP, for hosting. Thank you all for not taking a nap. Thank you for your tax dollars. Actually, yeah, U.S. government is very interested in this stuff right now, and so you're paying for this, and I hope you enjoy what you what you bought. Yeah, I'm going to tell you about chaos. Specifically, how we think about chaos in the quantum world. I'll assume you're all experts in what John told you. There will definitely be connections to what Matt told you at the end. And what I hope to convey through essentially pictures is some flavor of the kinds of physical phenomena we're thinking about and how we as physicists actually reason about them and calculate. Okay. So the place I have to start before I talk about quantum chaos is classical chaos. So here's classical chaos. The butterfly effect. You all know the story. The butterfly flaps its wings, and then somewhere a day later and a mile away, a tornado occurs which destroys the house. In this case, this is a nefarious butterfly, so it's using its power for evil. We also want to use quantum chaos to understand the physical world. First of all, it's a phenomenon that's ubiquitous, that occurs in nature almost everywhere. So that's reason enough to understand it from our point of view, at least from my point of view. But it's also crucial for many other things. So, for example, the way that if you jumble a system up, it relaxes down into a state where everything's settled down and kind of uniform. That's called thermalization. That underlies the functioning of thermodynamics. That has to do with chaos. The transport, the motion of electricity and heat in a physical system, that has to do with chaos, because it has to do with the scattering of particles. Even black holes have something to do with chaos, as we'll see at the very end of the talk. Okay, so it kind of appears everywhere. As Veronica said, it sort of touches many different subjects. My own background was condensed matter physics, physics of materials. But now I do quantum information, I do gravity, I do all kinds of different things. And you'll see lots of different examples of this. So what it is, a little bit more quantitatively, this is something called a Bunamovich stadium. Bunamovich is still alive. This is a very old thing. It's just basically a domain, some region, where you have walls, and these are a bunch of particles. You can't see them individually yet. You'll see them individually in a second. But I start them out with very nearly the same initial condition. That's the small change. And what they do is they just move around freely in this stadium, and when they hit the wall, they bounce off perfectly. That's the rules of the game. Very simple. And I'll just show you what happens. So they all start out in a line. I let them go. They bounce, start to spread out, spread more and more. It's going kind of crazy. At this point, if I stopped one of this movie and picked out a particular particle, you'd have a really hard time telling where it came from. And in fact, after a while, it looks like every particle can more or less be anywhere, more or less randomly, right? And this is actually, if you like, what underlies the assumption in statistical mechanics that things, all sort of possible things with the right kind of conditions can happen. This discussion of Boltzmann's, not Boltzmann's equation. Well, that's what's going on here. Chaos makes that happen. Okay. Now we want to understand this effect, but when there are quantum rules, and so the question we want to ask is, well, when the butterfly flaps its wings, that seems like a small change, but that's actually a huge change. There are lots of atoms moving a great distance in space compared to their natural size. So what's the smallest possible change that you could make to a physical system that would distinguish it from its previous state? Well, that would be like looking at a single atom and flipping that atom from being spin up to spin down, or from ground state to excited state, or any of these other little small changes that you heard about in John's talk. That brings us to this picture. So the simplest thing you can do is classically would be to flip a bit from 0 to 1. That's like changing one elementary unit. Quantum mechanically, as you heard, you can imagine changing a qubit from being in one direction to a different orthogonal direction, from being 0 to 1, from being up to down, from being heads to tails. And you do that for a single particle. That's sort of the smallest possible change you could imagine making in your system. And the claim is, nevertheless, that this single tiny change can still grow via chaos and ultimately lead to the whole system being completely different than it started with. The reason why we care about this phenomenon, apart from the fact that ultimately the world is quantum mechanical, and so we have to understand this, to understand the deep structure of the behavior of matter, for example, is that as pictured in this image, this is an array of beryllium ions. So you take the atom beryllium and you remove one electron, so it has one excess positive charge. Then they have a strong interaction via electricity, and they can form a crystal. This is a crystal that has been made in the lab of John Bollinger in NIST in Colorado. This is an array of about a little more than 100 of these ions. And each of these little blue things is one of these qubits. So we have this array that we can make, at least John and his students can make. I can't make it, but I can certainly think about it. We can control it, we can do interesting things with it, and it's fundamentally quantum mechanical. It can be isolated, it can be such that you don't look carefully at it, and so it stays in its sort of natural protected quantum state. And so we can explore the question of what happens when you, say, flip a single one of these ions from up to down, how that affects spreads over the whole system. And of course, when we're doing that, we have to take into account the rules of quantum physics. For that purpose, let me just remind you, you've sort of already seen some of the weirdness from John, but here's one slide about it. You sort of roughly know that maybe that what's special about quantum particles is they kind of can't make up their mind. They sort of want to like try all the options, like they want to go left and they want to go right. And there's interference of those two possibilities, just like the interference of waves, or at least similar to the interference of waves. And so if you had like a single hole electrons can go through, well, they go through that one hole with certainty. But if you have two holes they can go through, then they go through each of those two holes with some probability, and you can have some kind of interaction between those two possibilities. You can calculate different probabilities for the electrons to be at certain places, and you can get interesting interference patterns, as seen here. Okay, this just to give you some rough flavor. What's exciting is that when you put many of these particles together, as I showed you in the previous slide, you have a lot of complexity. So here, this is actually the same kind of thing John told you about. In the background here is the cosmic microwave background. So imagine filling the whole visible universe with hard drives, right? This is like the most possible information you could ever store about anything. Well, if you took all those hard drives and you tried to write down the state of a bunch of qubits, well, that would be 10 to the 97 bits is what you could store with the current, that was calculated like maybe a year or two ago, so that might be a little bit bigger now, but not much. That can only store the state of a few hundred spins. So evidently there's some extravagance about these quantum systems, some richness, some complexity that's not easy to understand, to write down, to think about. So that's why it's hard. But it's also exciting because in all that richness, there's sort of a lot of new possibilities, new kinds of physical phenomena, new possible technologies, new ways of understanding different aspects of nature. So this is actually a nice artistic cartoon that I like. It was actually taken from an article, a polemic, saying that quantum computing could never happen. This is supposed to be the machine that Google made that did the supremacy experiment that John told you about. And I actually think this picture is very hopeful because it looks like there's sort of a cloud of possibilities here, and maybe we're going to learn about like planets and they can just affect everything. Yeah, question.
Sorry, just when it says sufficient only for a few hundred spins,
yes.
What does that mean?
That means if you wanted to write down the complete quantum state, so write down the probabilities for all the different possibilities, all the different heads and tails for these bunch of coins, you could only do that for about 100 coins or 200 coins, and then you wouldn't have enough space to write down.
So the spin is spin up, spin down, for instance?
That's right, yeah. Yeah, sorry, I may use the spin qubit language inadvertently, sort of back and forth. That's just, well, it's hard to think of all the things that you forgot you never knew. So, let's talk about the main subject, which is the quantum butterfly effect. There's a thought experiment. It may sound silly, but bear with me. The idea is, think about, you have a VCR. People here still remember VCRs, some of you. You can like press fast forward and rewind. So you can run time forward, that's this orange curve, and you can run time backwards, that's the purple curve. And if you just fast forward and then rewind, you get back to where you started from. Nothing happened, right? That's what this picture denotes. You start there, you go forward in time, then you go backwards in time, and you end up at the same place. The thought experiment is what happens if you went forward in time, made a very small change, that's your butterfly, and then you try to go backward in time again. Well, at first you'll kind of like roughly cancel because most things are the same. You've only made one small change. But the whole idea of chaos is that small change will spread. It'll kind of infect the whole system. It'll go everywhere. And eventually you'll end up, after a while, at some totally different place. So this is kind of the effect we want to understand. Let me give you another analogy. I hope you've all had the pleasure of trying to assemble IKEA furniture. This is a particularly nasty example. I'll let you figure out whether that's possible. So, what's the analogy? It's like you got to step 34 out of 34, the final step of making your cabinet. It's a really nice looking cabinet. You're very happy with it. Then you see, there's a screw that off to the side. And you're like, what happened to this screw? Is the screw important? You look over the directions. There's no word, so it's very complicated. But you eventually figure out that you missed a screw in step 2. And, okay, well, what can you do? Basically, the only way I know how to do it is to undo all the steps back to 2, put the screw in, and then rebuild it again. And that's the butterfly. On the other hand, you could say to yourself, well, this looks more or less like a cabinet. It holds books. Let me not worry about it. It looks like a cabinet. Let's just treat it like a cabinet. Even though it doesn't have this screw in it, it's still functioning the same way. And that's this idea we saw in that butterfly demonstration that at the end of the day, everything can kind of look the same, even though the microscopic state was very different. Let me show you how it works in an actual system. I'll show you what's called a space-time diagram. So this is space. Each of these black lines will be one spin or qubit, one 2-level system. It has 2 options, 0, 1, up or down. Time will run up. And when you just have a straight line with nothing happening, that means the particle is just sitting there doing nothing. It's staying the same. And there'll be 2 ingredients. One ingredient is the forward in time evolution. This is what we call a quantum circuit diagram. What these orange boxes mean are there like interactions between these neighboring particles. So these 2 qubits can talk to each other somehow, like the gates that John mentioned. These kind of interactions could create entanglement between these 2 particles. So you could create some entanglement between these 2, and then this layer could spread that entanglement out 2 more steps and keep spreading it out further and further. That's the forward. There's also the backward. I'll draw that in purple. And the rule, following our rule that if you go forward and then backwards nothing happens, is that these 2 things will cancel if you don't put anything in between. So now I'll show you my PowerPoint skills. They cancel like that, and you get back to nothing. Okay. I know, right? It's pretty amazing. That's actually how it works. Okay, well, let's put our little butterfly in there. Right, this is the fly in the ointment. Now I want to cancel again. And most of them can cancel. It's sort of forward and backwards, like we said. You haven't affected much of the system yet. But you see this little bit and this little bit, well, it causes these 2 neighboring ones to talk to each other. And so once I know a secret and then I start talking to you, it's really hard to keep that secret secret. I tell you something, and then you know the secret too. And so now I should color that blue, because now the information or the blockage or the perturbation or the butterfly flap is like affecting both of these 2 sites. Now I do it again, try to cancel some more. Well, now I've got sort of 2 blockages, and these 2 blocks are going to get messed up, and now it's on 4. I keep canceling, and you see how it grows. It just keeps growing. So this tiny effect, which affected just a single spin or a single qubit, already, after just a few layers of this evolution, of this time evolution, starting to affect more and more of these spins. And if you let it keep going with time, it'll just affect more and more until it affects everything. And that's the chaos. The chaos is spreading from this single change to the whole system. Now, here I showed you a case where the interactions between the different spins were local, between neighbors. So it's like you're talking to your friends in your row of chairs. It's also possible in physics to arrange situations where you can talk non-locally. This would be like talking on a phone to someone. In that case, we could draw a picture like this. Now I'll show you snapshots at fixed moments in time instead of showing this movie because I just can't animate that well. You have a bunch of qubits now. This is a fixed moment in time. They're all arranged in some kind of random way. And they can interact in a sort of kind of random way. So, for example, those pairs could interact, or those pairs, you could choose. And there are actually physical systems where this is a good approximation or a good caricature of the way that physics actually works. I'll actually tell you about one of them a little bit later. So we can play our same game. We can put our fly in the ointment, our butterfly wing flap. And now let's say that was the first interaction pattern. Well, then you see that whatever the butterfly's done, it's going to spread to that site there, right? Because they're coupled. So I'll make it blue. Now I have a different random pattern. Now this one's got some problem. It's going to spread to that one. This one's going to spread to that one, like that. Another random pattern. What you can convince yourself of is that the affected region will double with every step. So in this case, the perturbation is spreading extremely rapidly. It's doubling every time. And so after a very, very short time, it can spread over the whole system very efficiently. So this is another kind of example where you don't have the constraints of only talking to your neighbor, that the perturbation can spread even more quickly. Okay, now how do we probe this? What do physicists actually calculate? They calculate something called a commutator. That's just a word. What it means is they test the extent to which doing this complicated set of operations, the extent to which that matters whether you do it before or after you do some other simple operation. So that's what this red thing means. And so you imagine you could do this complicated blue stuff. Remember, time goes up. So you do some complicated blue things here. And then you do some red thing later. And you want to know whether it matters whether you did the red thing at the end or at the beginning. And here, that simple red operation, which just touches a single qubit, it's only on this black line with no blue on it. And so it can just move through and nothing happens. And so doing before and doing after is the same. But you can imagine that if I put it here, say, or even further in, that it would have trouble. It couldn't quite get through because there's some blockage. The blockage is kind of weak here. There's only a little bit of a chance that perturbation has spread that far. But as you move inward, it becomes stronger and stronger. And eventually, the perturbation is so strong that you essentially can't get through here at all. And so we can detect, then, the spreading of this perturbation by probing it with these simple probes and seeing whether the ordering matters. Okay. And this is actually what people calculate. I just want to show you this because this is what we actually compute. Except there's one little rub. Here I showed you everything as if it was sort of definitely happening. There was a definite single thing that occurred. We know that's not right in the quantum world, that there's different possibilities. We already discussed that with electron. So the perturbation has some possibility that it doesn't spread at all. It has a possibility that it spread all the way to this point. And in fact, the likely thing is that something in between happens. And we want to calculate what that likely thing is, because that's what we can actually measure. Here's some equations, just to give you a sense. It's complicated. It's a differential equation. So there's time. That's a partial derivative with respect to time. There's a bunch of terms here. For even a few hundred of these spins, there are more equations than there are grains of sand in all the beaches of the world. But nevertheless, we have some understanding of what's going on here. There's some structure that we can utilize to calculate. And we can calculate. This is one of those cases where it's a hard quantum mechanics process in principle. But in practice, there's some structure, there's some physics, some element that we can use to understand with our classical brains what's going on. So we can process all this mess. Happy to tell you about it afterwards if you really want to know. It's a bunch of rate equations, essentially. And what we can get out are precise pictures for how this perturbation looks. So if I plotted, for example, the strength of that perturbation at a fixed time, this is how it would look. There would be a sort of core where the perturbation is very strong, it's fully developed. There's some kind of crossover to an outer region where the perturbation is weak, where it hasn't spread yet. And this crossover we can also calculate accurately. Similarly, if I make a space-time picture, where I look at the contours, the sets in space-time, in distance and time here, where the strength of the perturbation is roughly constant, we'll find that those look like lines, which means there's a speed. A fixed unit of time and a fixed unit of distance correspond. That corresponds to a speed. In this case, the slope of that line is 1 over a speed, and we call that speed the butterfly speed, because it's measuring the extent to which this butterfly effect propagates in space. Okay, so at this point, I think there are 2 questions that we need to ask. I've kind of given you a physical picture of the effect, and these physical pictures are pictures that I use in the beginning of all my actual talks, so I think this really is a good cartoon of how it works. I won't show you in detail the result of this complicated mess, but we can do that too. So what I want to tell you now, though, is how we measure this in the lab, how we can actually see it directly, experimentally, and then how it also manifests in other physical properties. So that's where we're going to go next. So let me tell you about measuring quantum chaos. This subject is a lot of fun. It involves time travel in a precise sense that I'll make clear later. It's not the kind of time travel you're thinking about, but something more reasonable, but still very interesting. It actually goes back many years, at least to the 50s, and if not earlier, in what are called spin echo experiments. These are experiments where you have some, basically the way an NMR machine works, it utilizes the principles that these spin echo people discovered. And in particular, there was a guy called Erwin Hahn who discovered this spin echo effect, and he explained this in a beautiful way on the cover of the Physics Today from 1950-something. And the idea was, let's think about a bunch of runners. Here's my runners, and they're running on a circle. What is this circle? This circle is actually the 2 dimensions that John told you about, the 2 orthogonal directions that can describe the 2 states of your quantum system. So each of these runners is a different atom, or a different qubit, or a different spin, and it can move around this circle, it can move around in its space of states because you've imposed some external influence on it, which causes it to do so. And all the runners are lined up initially. That's like all the runners spin up. And they have the property that they all run at different speeds. So that's just a characteristic of these runners. Maybe they had different trainers, or maybe some of them are having bad days that day. I don't know. For whatever reason, they run at different speeds. And so if the referee, this little person here, shouts go, they start running. They run around the track. They're running at different speeds. After a while, they've run, this is B, then C. After a while, they've run a lot, and they're kind of spread all over the track in a very haphazard fashion. So at first, they were lined up nicely, and everything looks collimated and simple. At this intermediate time, they kind of spread everywhere, and it looks like you just have people kind of randomly all over the track. But the referee can shout. Maybe the referee stands in the center so that the referee can talk to everyone at the same time, no matter where they are. The referee shouts reverse. And what happens? Well, they dutifully turn around and run backwards. And they're all at different places, but they're exactly at the place they had been given how fast they can run. And so if they run backwards with the same zeal they ran forward with, lo and behold, they'll all come back together and collimate and realign. So if your experimental measurement is saying how many runners do I have in a little slice through this ring, it would start out high and then become very small, but then when you do this reverse signal, it would become big again. That's the spin echo. Here it is again with my PowerPoint skills. PowerPoint can actually do this experiment. It has a timer in it. So they run forward, they have different speeds, then you shout reverse, and they run backwards, and lo and behold, they all line up again. And that's a real experiment. It really is timing them. They have a fixed speed. Here's the actual data from his paper in 1950. These peaks are looking at this sliver and asking, are there lots of runners there or not? And you can see there are these big peaks that repeat over some long period of time. But still, you say, okay, you're very observant. You say, well, still something's decaying ultimately. After a while, you don't get back. But what is that? Well, the problem is that I can say go forward, and I can shout reverse, and I go back. Well, this time they don't get back to where they started from. So what happened? Well, lots of things could happen. For example, maybe this runner at the bottom had a tailwind, so they got a little bit further on the way back, so the wind changed. Or maybe these two runners bumped into each other, and via that bump, they scattered and they went more slowly for a little while. So in other words, either by external influences or via uncontrolled interactions between your runners, the reversal process can fail to be perfect, and you end up not really collimating things backwards again. And so the decay you saw here, this decay is related to the decay of these uncontrolled processes that you don't have access to. So the challenge for us then is actually to control these processes in such a way that we can do the reversal while keeping the system isolated and controlling all of these interactions. Because we saw before, we wanted our qubits to interact. We want to have interactions. What was nice about this runner thing, the reason why they could do it is because the runners didn't talk to each other. They were all non-interacting runners. We want to study interacting runners. That's how you get many-body chaos. The chaos of many interacting runners. And so what we need is a time machine of sorts. I call it an inverse DeLorean. The reason is that the DeLorean has the funny property that the people inside it were left the same, but the outside world went backwards in time. That's impossible, but as far as we know. But what you can do is make a machine so that the stuff inside the machine effectively gets rewinded, whereas the stuff outside is staying the same. In fact, you're using energy and entropy from outside to make this machine work. And one of the things that you could in principle do, in fact, what the Google computer did was a simple model of quantum chaos. They actually ran this kind of random dynamics forward. And they could, in principle, run it backwards in time and try to measure some of these things. They haven't done that yet, but that's one of the candidates that physicists would like them to do to study these effects. But there are other physical systems where this is possible to study. One of them is this picture I showed you at the start with the array of beryllium. So let me just give you a flavor of how this works and the kind of pieces that are involved here. So this is John Bollinger's lab in Colorado. There's a gigantic magnet here. This is like a casing for this 4.5 Tesla superconducting magnet. And inside this gigantic magnet, there's this little cloud, this little blue thing. That's that blue cloud you saw before. This is about 2 centimeters in size. And what they can do is, in addition to having this gigantic magnet, they can shine lasers on this system from the sides. And they can use these lasers to control this little array of ions. How do they do that? Well, here's a picture of that crystal. So I showed you that crystal here from the top. Now I'm kind of looking at it from the side. You see that this array, in this case, it's a triangular crystal. Each of these little blue things has a spin on it. That's the up or down, the 0 or 1. And like any two-dimensional sheet, this can vibrate. It has oscillations. It can wiggle in various ways. And those vibrations have some frequency, and you can actually drive those vibrations using lasers. Just in the same way you could drive your atom between these two 0 and 1 states. If you shine the right color of laser, you can also drive the vibrations here. But because the whole sheet flexes like this, the flexing depends on all of the spins at once. And so in this way, you can make every spin here talk to every other spin in some more or less uniform way. This is actually how you can engineer something like that all-to-all interaction where everyone could talk to everyone instead of just your nearest neighbor, by coupling these spins to the vibrations of the mechanical sheet itself. I say a sheet, it's not really a sheet, it's just the positions of all these particles. But it's something that can vary in time. It has this vibrational motion, and you can couple to that. So I won't, of course, explain any of the real details of this. But suffice it to say, you can, by applying lasers and other technological equipment, cause these spins to interact with each other. And moreover, you can actually cause them to interact in such a way that you can effectively reverse time. The way you do that is you can change whether the spins prefer to line up or to anti-align. That's called ferromagnetic versus antiferromagnetic. It depends on the sign of the energy. If the energy for them to align is positive, then they want to anti-align, and vice versa. And it's possible by changing the color of these lasers to actually change whether they want to line up or want to anti-align. And because of the way quantum mechanics works, that changing of the sign of the interaction is actually equivalent to running them forward and backwards in time. Just in the same way that kind of reversing the motion was like undoing the trajectory of these runners. Okay. And they're actually doing these experiments. They're trying to measure the kind of quantities I showed you before, these commutators that we talked about. And they have actually done some measurements. So far, they've not done a measurement that we can't understand using our classical computer, so we're not at that limit yet. But we're very hopeful that soon they will be there. Yes, question? This is just, I think in this case, there are just two different laser fields coming in here. So it's the angle between them. Yeah. They use beryllium because it's light. It's a relatively light atom, and so it makes these oscillations have a relatively high frequency. And because they have a high frequency, you can then more easily cool down to a state where they're not highly excited, and you can control them effectively. A lot of fun details there. Okay. So that's just one flavor. I would say there's, order 5 or 10 experiments actually running right now trying to probe this physics. As I mentioned, the Google computer could be another one. They're trying to get them interested in it. Actually, that thing about probing wormholes that John had, well, I'm on that paper. And it has to do with this stuff, actually. These wormholes are all related to this chaos stuff. I won't explain that, but I'm happy to talk to you about it afterwards. So let me change gears now and tell you about how this physics manifests in maybe more familiar things. And the first thing I want to talk about is the problem of speed limits. Okay. When I was a kid, I would wonder, what does this sign mean? Do they bomb you if you go too fast? I guess they just time you. If you they see you start here from the airplane, and you go past this other point. If it's too fast, and they know somewhere by the intermediate value theorem that you had to have sped somewhere in between. So even the police use a little bit of calculus. What is this? Anybody know? It really hurt me to write this, if that's any help. It's the speed of light in miles per hour. I know, it's terrible. It should be equal to 1. I spend most of my life in the place where the speed of light is 1. It's a nice set of units. So this is the speed of light in miles per hour. That, as far as we know, is sort of the fundamental speed limit for the universe. Nothing can go faster than that. Although, if you were paying attention in Matt's talk and you learned that geometry emerges from something more fundamental, you might actually wonder whether this speed limit is itself fundamental. Maybe that too emerges from something simpler. And we think that's true. But I won't tell you that story today. I'll tell you a different story. You know very well that although this is the ultimate speed limit, it's not practically relevant for your life. You don't normally get very close to that. There are lower speed limits that restrict your motion. And we'd like to understand the physics of these speed limits. These speed limits occur all the time in physics. You have systems that could in principle be moving at some speed, but for some reason, things move much more slowly. And what I want to show you is that actually the physics of chaos can have to do with this. It can inform the way these speeds work in your system. Here's the kind of thing we're thinking about. this gentleman is experiencing an emergent speed limit due to the strong interactions of these animals. We're interested in my group in the case, what happens when these animals are quantum animals, whatever that means. Their motion is quantum mechanical, and in that case, they can inhibit the motion of these things. Okay, well, we already saw a picture that has bearing on this. It's this picture, where my butterfly flapped its wings on a single spin, and that effect somehow propagated outward. But as I said, these contours here in space and time are more or less straight lines, which means that you have some increment of space for some increment of time. So there's a speed there. There's some kind of velocity. And so what we're understanding now is that this speed that you compute from chaos is like an effective speed limit, an effective upper bound on how fast things can move in your system. So there's an ultimate speed limit, the speed of light. But in practice, because of the way the interactions work in your particular system of interest, it may be the case that there's one of these emergent speed limits. And it turns out that chaos sort of moves as fast as possible in some sense. It kind of goes as much as it can go. And so if you measure the speed of chaos, you actually learn then an upper limit, an effective upper limit on your system. So just, for example, think about the air in this room. There's a speed of sound, which depends on temperature in some specific way. And for the purposes of me communicating with you, that speed of sound is the effective speed limit. Of course, we could communicate via light somehow, which would let us do it faster. But in practice, that's an upper limit on how fast we can talk to each other. And so the same kind of thing happens here. You can actually show that in a very precise sense, information that you inject here, whether this, say, qubit or spin is 0 or 1, that information can spread out in your system, but it can't spread any faster than this butterfly speed. So you really have an emergent kind of speed limit that's set from these chaotic strong interactions. So just like this gas of sheep here, you have then, because of these strong interactions, an effective speed limit that's controlling your behavior. And in fact, this speed limit can be very dramatic. It can go all the way to 0. There are physical systems called localized systems where the interactions are so strong and so random that essentially nothing can move. Everyone gets frozen in place. And that's another case where chaos is playing a role. What's happening there is chaos is failing. This spreading phenomenon is no longer taking place, and you end up with your information, with your perturbation localized in space. And that's one of the things that people in my field care a lot about, the way this localization physics works. Okay? Any questions about this picture? Yes?
I guess it was in the big picture. From an information standpoint, do we want this spread of chaos or information to be small or large? How does it affect your system in terms of the noise? I don't know, does it connect with the noise you get from quantum?
Yeah, good question. From some point of view, you don't necessarily want it one way or the other. You just want to know how it goes. If you want your system to not lose information, you might want it to be slow. So this localized system is an example where people want to keep the information in one place so they can operate on it. And if the information is spreading out everywhere, then that's doing a bad job of keeping it in one place. So you want to actually maybe minimize this velocity or control this spreading.
Well, actually, are there some assumptions on how your qubits are being distributed in physical space here? I mean, are they uniformly distributed and kind of close together?
Yeah, there definitely are assumptions of that type. I'm assuming that they're close and that these are strong interactions. And that they have a certain character. They have this chaotic character. So there are other kinds of interactions that you can have. There are physical systems where these boxes are not chaotic boxes. The underlying interactions are not chaotic. And then what happens is you may spread, but the picture looks different. For example, instead of having, well, I won't draw a picture, but instead of this like core where you had strong perturbation, it could actually drop to 0 again inside. That would be more like a system of free particles. So here, it's really fascinating. The information is not in any one place here. It's kind of spread uniformly over the whole piece. It's like if you have a single electromagnetic wave or a single particle of light, a photon, carrying some information, that can be at a more or less localized place in space. Not perfectly localized, but reasonably well localized. And you can, just by looking at that place, by looking at your antenna, you can get the information out. But here it turns out, one of the properties of chaos is that if you look at any one of these little small qubits, you don't see anything. It looks just like noise. But if you look at the whole thing, and if you could do a very complicated quantum operation, which actually just amounts to reversing all of these things, then you can figure out what your butterfly did. So this is a case where you're really spreading entanglement everywhere. So this bunch of spins here, they're all entangled in some very complicated way. So that if you look at any single one of them, it's like the head or tail that you get randomly. You don't see anything useful from that. But if you look at all of them together, you can decode what the butterfly did.
But aren't they under the rule that they have to obey that first speed limit to even be on that graph?
That's right, yeah. So this speed limit determines how far this information can spread out.
No, I understand
Yeah.
that. But I'm just saying that they can't have any randomness to them because they have to obey the rules of being a qubit there initially, because nobody changed the rules.
That's right. If I understand correctly, no one changed the rules, but these boxes here can generate randomness, effective randomness, because they can generate entanglement.
Okay.
So this box here can make a state where originally your two coins were uncorrelated, but after this box is applied, they're correlated. So if you like, this is, what was his name, Don from Denver? Each of these boxes is Don from Denver, and he's making these entangled pairs. So actually, Don from Denver is very ubiquitous. Nature supplies us with entanglement everywhere you look. It manufactures it and encourages it because of these interactions between the particles. The challenge is to control it. The problem is that it kind of goes everywhere. And then once it goes everywhere, you can't do anything with it. So you want to orchestrate it. That's the challenge of quantum computation. Yeah?
What's the role of time in all of this? Well, I mean, is it constant? You're assuming that it flows or doesn't flow?
Yeah. So,
All chaotic systems?
yeah, that's right. So what I'm showing you is a kind of, I'm showing you the behavior as a function of this forward-backward pattern. So you go forward for some amount of time, then you go backwards for the same amount of time, and I'm studying as a function of that time interval, which is like 1/2 of the total amount of time you run for in the experiment. So I'm sort of distinguishing, if you like, experimental time, which is what you in your lab actually experience, the flow of real time, from the effective flow of time experienced by this system, which I can control and manipulate and arrange so that it goes forward for some time, it goes backwards for some other time, maybe it even stops evolving. So for example, if you go back to this picture here, if I turn the lasers off, then they just stop interacting with each other and they're sort of frozen in place. And whatever quantum information is there will live without changing for a while. Eventually something will happen and it will decay and they'll talk to the environment and bad things will occur, but for a while the information will be preserved. So what we really have in mind is that we can kind of control the dynamics in this way. So a physical system, like if you want to understand the behavior of electrons in some metal, which is one of the things we'd like to do, of course it just goes forward in time. We can't control it at the right level to do this forward-backward business. But nevertheless, at the level of a thought experiment, as a conceptual idea, we can think in these terms and it illuminates the physics for us. So in particular, I'll mention one more thing before I go on, which is that this speed here might also have something to do with the motion of electricity or the motion of heat. So that's one of the fundamental things we care about in the physics of materials is how fast or how easily electricity and heat flow through a system. And if you have some kind of speed limit on how fast things can move, you might imagine that's also relevant for the motion of electricity and charge. Electricity and heat. And this is one of the open questions in our field, actually, is trying to understand whether this speed, this chaos speed, has anything to do or rather how it precisely interacts with or affects those other physical quantities. Because those are easier to measure, so if there was a direct connection, that would be very nice, because then this sort of conceptually nice thing would directly impact something that you can go and measure in your lab easily. Okay, I have about 10 minutes left, so I'm going to talk to you about one more topic, which is black holes. Here's a pair of black holes, artist's conception. And so now we're going to require you to remember what Matt said. First thing, we'll get to that in a second though, well, we knew black holes were real, but we've really sort of really seen them now directly. This is the now famous observation by LIGO and Virgo using this gigantic detector here in the desert of eastern Washington. That's Hanford. Of the merger of two black holes into one big black hole. This is them coming together, they merge, and then there's like a ring down effect where they sort of stop vibrating and then reach a quiescent or equilibrium or sort of steady state. And the beautiful story here is that GR perfectly predicts the behavior of this collision. You can model it very well. This is part of the evidence that general relativity is a great theory. And, you know, this instrument is fantastical. I actually visited this thing once, like 15 years ago. And you went to the control room, and, you know, you could see on the control panel, they show you these spikes, and they're like, that's a tumbleweed hitting the beam pipe. Or this is traffic in LA in the morning. You could see all that. And that was noise. They had to get rid of all that to actually see this super tiny signal that comes from these little itty bitty ripples in space-time from whatever, 10 billion light years away or whatever it is. So it's pretty amazing. And we would love to understand what's going on here at the level of quantum mechanics. We want to understand the quantum physics of space-time. That's what Matt talked about. But we can't. It's too hard, at least for me right now. So we play the trick that Matt played, which is we retreat to this funny universe that doesn't describe our world, but is easier to understand and calculate. This is the retreat to anti-de Sitter spacetime. This is a picture of space in anti-de Sitter spacetime. So this is like the circle that Matt drew. This is a famous print of Escher. The idea is there's a metric or a sort of a size in which all the fish here are the same size. So even though they're drawn small, they're actually all the same size. And that can only occur if it's drawn on if it's a flat description of something which is ultimately curved in space. And you kind of see the fish are getting smaller as you go out, and actually the edge here, that's the boundary Matt was talking about, where you have your quantum mechanical degrees of freedom that somehow generate effectively this hologram of the interior. This empty space describes the lowest energy state of my quantum mechanical system, where there's sort of nothing there. But we can get black holes by heating the system up, by exciting it. So we take our quantum mechanical system on the edge and we put a candle under it, or a Bunsen burner or whatever, and it gets hot. And the description of that in this interior, what Matt mentioned, is that there's now a black hole here. That's this black thing. And what's nice is that this black hole is mysterious from the point of view of the interior of this space, but from the point of view of the exterior, it's maybe a little bit less mysterious. It's just a quantum thermal state, a hot state of some quantum mechanical system. And that's something we understand a little bit about. But at the same time, that black hole has properties that are similar to, at least in some ways, the black holes we see in actual nature. And so we might hope that at least for certain conceptual puzzles or certain questions that have a general answer, you might be able to learn the answers by studying this toy model, even though it's not the thing you really care about in the universe, but in this simpler setting where we can ask questions that make sense. There's another exciting possibility mentioned by John, which is that given a quantum computer, we could actually try to engineer in that computer. We could make the computer mimic the boundary dynamics here, this boundary quantum system. And in so mimicking that, we could effectively mimic this hologram and thereby study, again, the black hole in this mimicked way on our computer. So we could actually do an experiment, if you will, which effectively probed this physics. So that's why it's exciting to us. We could actually probe it in experiment, and it's at least an interesting toy model, a spherical cow, of the real thing. Okay. And now there's one piece of physics I need to tell you about this thing, which is that if you start here and jump in, you start to fall towards the black hole. That's because the black hole gravitates. It pulls you towards it. And the basic fact about this falling in process is that the energy, as you fall in, doubles every unit of time. So as you get in, the energy keeps getting bigger and bigger and bigger. That's falling into the black hole. You're getting accelerated more and more. And you have a very high energy by the time you reach near the horizon of this black hole. And it turns out that one of the beautiful connections is understood in the context of this connection between space-time and quantum mechanics is that that doubling is precisely a manifestation of chaos that I told you about before. So you remember this picture where I have my perturbation and the interactions were such that this perturbation doubled its effect every time step. That doubling effect, we now understand, is precisely the same as the doubling of energy as you fall into this black hole. I won't explain to you how that works. I just tell you that that's the way it works. And so once again, our understanding of the way chaos works in these complicated many-body systems of many qubits actually informs us about the interpretation or meaning in the quantum mechanical language of something like falling into a black hole. So this is one of the reasons why we're excited, because now we understand something about chaos. Maybe we can understand something more about what it means to fall in, maybe what it means to be inside. And that's indeed one of the things that this conference the last 5 days has been about. It's been partly about using chaos and related ideas to understand this black hole, what it means, and how to think about it, including its interior. Okay, so that's about all I wanted to say. Let me just flash an outlook. So the physical phenomenon I told you about today is what I call the quantum butterfly effect. It's the quantum version of this classical butterfly effect, where you make a small change and it spreads over the whole system. I try to give you a few pictures that are actually qualitatively accurate, the way we actually think about them as physicists, which shows how this spreading effect works. But this is really just the tip of the iceberg. The study of quantum chaos actually has a very long history. There's been kind of a renaissance recently in the field. The study of quantum chaos goes back a long ways, but thanks to all these new ideas from quantum information, these new experimental possibilities I showed you, these ideas from gravity, there's been a real revitalization of the field, a lot of new ideas, a lot of new possibilities that have come in. One of the things we've been trying to do is understand how the new things relate to the old things, which are still very interesting. But it's also just exciting to take these new things forward. So to take these experiments I showed you and really try to push them to a regime where we can't understand the physics, or we can't simulate the physics using a classical computer, where we really need something intrinsically quantum to understand. And because there's so many connections, we sort of think there's probably even more hiding out there. And that's why we're excited about this field. It gets to bring together many-body physics, gravity, atomic physics, these crazy experiments involving effective time machines, and all kinds of other fun stuff. And so with that, I'll say thank you. This is a list of my collaborators in this work for the last many years. So thank you for your attention.
Thank you, Bren. Questions?
If we go back to the picture that you had of the Escher print and the fish disappearing,
Yeah.
you say that energy doubles per time.
Yeah.
I expect that time is sort of not represented directly in that picture.
Yeah, this is like a fixed moment of space. Yeah.
So does that mean that...
Sorry, a fixed moment of time. Yeah.
Right. So that for an actual black hole, if you just wait and it absorbs a certain number of joules, in the next unit of time, it'll absorb twice that number of joules, and it keeps doing that forever?
Well, this is an approximation where the black hole is not changing.
Okay.
In fact, the whole energy is conserved. So it doesn't like ultimately just keep increasing its energy. Like the black hole is accelerating this thing, but the total energy is conserved. Does that answer your question?
Almost. I'm just wondering why the universe hasn't already been swallowed up. You know, if there are black holes which are doubling energy per time, how come it hasn't absorbed?
Well, it's not the black hole. It's this particle that's falling in.
Oh.
Yeah, the whole black hole. Yeah, sorry. Yeah, the black hole is not doubling. It's this this blue to red. It's heating. You know, it's sort of getting more energetic.
That particle's energy is doubling as it approaches the black hole. Thank you.
Yeah.
Other questions? So how far can these experiments run the time backwards so far?
Not very far. There's like a natural unit of time, which is how much, like one of these layers of interaction. And they could probably do the best, maybe 10 layers or so before it's just total garbage. So it's still a work in progress, but it's very exciting. It's comparable to this Google machine. What they actually did was these kind of layers. That's like literally what they did, where the layers were chosen, like each of the interactions was kind of just a random choice. And they did, you know, order 10 layers. So this is kind of the state of the art now.
So if the infalling energy doubles per unit of time going into a black hole, but the black hole is affecting the time gravitationally,
Yeah.
what does that unit of time mean?
Yeah, this is a good question. I mean, in fact, this is kind of a tricky business. That actually the way this works, it's really, you know, what we call a gravitational redshift effect, which is kind of primarily responsible for this. So like it's climbing out of the potential well of this gravitational field, which is like causing this energy. And so this doubling occurs in a certain natural energy, which is associated with how can I describe this? Well, as you alluded to, there's various different notions of time. And this doubling occurs in the energy as measured by certain notion of time. But there are other notions of time, for example, the time that this particle keeps with itself, where its energy is not doubling. Okay, so it's really the distinction between these things which matters in this case.
Other questions?
This morning, John talked about trying to keep the quantum computer from having the outside world affect it until we want to probe it and get the answers.
Yeah.
Is the work that you're doing related to, well, how do we turn that on and allow the outside world to affect it versus let's isolate the system and only let it do its computation?
Yeah. So sort of there's various answers to that. I mean, for one, seeing this effect that I talked about requires the isolation. Otherwise, if you like, there's too many of these like interactions with the rest of the world, and the entanglement gets spread out, and you lose track of this simple expanding behavior. So you need that isolation. But at the same time, so sort of studying this chaotic dynamics may help you understand how better to isolate or the kind of mechanisms that lead to a lack of isolation. And so, yeah, and then at the same time, when we have these isolated systems, that we can use those to actually study this effect. So we can compute using pen and paper or using classical computers what's going on here in some cases, but not in all cases. In fact, in most cases, we don't know how to calculate, precisely because it's a hard quantum interacting system. And that's exactly the kind of thing that we as physicists would love to be able to do with a quantum computer. I don't care about factoring numbers or whatever. I mean, it's interesting, but from here, the direct interest is I have a real system, like a metal, where I want to understand its behavior, or one of these funny superconductors that Matt mentioned. And the idea is I can use my quantum computer to sort of mimic or simulate the dynamics of that in a controlled fashion, where I can really access some of these things without all the difficulties of the dirt in the system and the sound and all this other stuff happening.
So I'm intrigued by this anti-de Sitter space that you've got here. It's obviously a model to hold a black hole. What you're pointing to is information that you can gain from it outside the event horizon in the space of the anti-de Sitter space. Is there anything you can learn about the black hole from this particular model within the event horizon?
Yes, there is. It turns out, for example, that if you look inside, there's space inside, in the simplest case. And if you look at that space, it keeps growing with time. So the longer you wait, the bigger it gets. So one of the questions in this business that Matt was talking about, the quantum mechanics to gravity, is what does the meaning of this growing space on the gravity side correspond to on the quantum mechanics side? And we have an answer to that, a proposed answer, not a for sure answer, but a proposed answer, which is that it's adding more and more of these layers, but after this perturbation has spread over the whole system. So imagine a fixed, large number of these qubits. Eventually, the perturbation spreads everywhere, and then it looks like, okay, there's nowhere else to spread. So what's happening? Is the system just quiescent now? Is it not changing anymore? But no, it's still adding layers, more and more and more layers. It's becoming more complicated. You would need to evolve longer and longer backwards in time to reverse more and more layers to take it back to something simple. And that increase in complexity, the increase in the amount of operations you would need to do to bring it back to somewhere simple, is our candidate for the interpretation of the growing interior of the black hole.
And is that data about the perturbations, is that data about the perturbations related to the radius of the black hole as it grows? I mean, can you make mathematical connections between the radius and the amount of complexity of the chaos?
Yeah, it's not that the radius is growing. It's that you kind of imagine this ADS is like a trumpet. So it kind of comes down and it stops at a ring, and that's the horizon. If you go past that ring, it's like you have a conveyor belt that just keeps getting longer and longer, and that's the adding of these gates. And it's as if this perturbation is being hidden deep inside the black hole, where it's really hard to find. And so if you go back to that picture I had of the cabinet where you had the screw, it's like the screw is just getting buried more and more steps in the past. And it's becoming harder and harder and harder to figure out if there was a screw there or not. That's kind of the idea.
Other questions? All right. Well, let's thank Brian again.
Thanks.